Hello? Oh, okay, it's working. Wow, that's a long delay. Okay, we'll work with it. This is an ENA final exam review by IEEE. Yeah, hey, so I can see you guys in the chat. If you ask questions there, that would be great. There's an enormous delay. It's got to be like 20 to 30 seconds. So it will take the delay until I answer questions if you ask it, but know that I can see it. As far as topics go, this is for Dr. Chu, right? Oops. And according to his website, the final is comprehensive. I do not have the time to go through everything, so I'm going to. Oh, it's Jeremy. Hey, I'm going to choose to focus on the latter half of the course. I should have already gone over the first half in the first test review. So the plan is to start with second order circuits, then move on to sinusoidal steady state stuff, Laplace analysis, op amps, and then we can do filters, but I don't know if Dr. Chu actually goes over them. So tell me if he does or doesn't. So this one I'm not sure. And then I can go back and review anything if we have time or if I feel like it. But this is my current plan. If there's something no, I know you guys do a bit of power. I'm skipping power because I'm not prepared to do anything on that. I don't have any problems prepared for power. So I'll just be doing this stuff. Sound good? And if not, I'll see it as I move on in 20 seconds when delay hits. So let's start with second order circuits. If we look at Dr. Chu's practice midterm, it doesn't seem like he makes these solve problems in depth. Okay, I didn't see filters on his practice midterm anyway, so I'm going to assume this is not important. Dr. Chu's testing to be more theoretical. It doesn't look like he makes you do any in-depth, like, math. But I'll go over these anyway. Second order circuits. Let's start with the types. Yeah. So let's start with the two types. We parallel. So first of all, second order circuits. These are your RLC circuits. They have a resistor, an inductor, and a capacitor, one of each, and they come in two flavors. You can have the parallel RLC or the series RLC, and I'll get the series one later. So the parallel RLC is when all three of them are parallel, obviously. So we'll have a resistor, a capacitor, and an inductor all in parallel, and that's your RLC component. What we're solving for is we're solving for this voltage right here, because all three components share the same voltage. So we will solve for that first, and then using that voltage, you could solve for any of the currents or anything else you want in any individual component. This is a second-order differential equation, hence the name second-order circuits. And the roots of the characteristic equation that describe this are these. You have S1 and 2 equals negative alpha plus or minus the root of alpha squared minus omega naught squared. And you may ask, what are these strange symbols? Alpha is 1 over 2RC. This is referred to as the Nesper frequency. Omega naught equals 1 over the root of LC, known as the resonant radiant frequency. And omega D, while not in the original one, comes up later, is equal to the root of omega naught squared minus alpha squared. Basically the opposite of this. And it's called the damped radiant frequency. And this is, and keep in mind, these slightly change for the series circuit. This is for the parallel. There are 3 solutions to the characteristic equation. You can have an overdamped circuit. Overdamped circuit is where the roots are real and distinct. And another way to say this, you can test this if W naught squared is less than alpha squared. So in this case, looking at our definition of W naught, we have if 1 over LC is less than 1 over 2RC squared, right? If this is true, your response is overdamped. And then the solution to your voltage across the circuit is V of t equals A1 e to the S1t, where S is, once again, these things over here, plus A2 e to the S2t. And you need to solve for your initial conditions using the initial conditions of the circuit. We'll get to that later. But this is the general Fourier response. Once you get to this point, the only things you don't know are A1 and A2. For an underdamped response, this is when the roots of the characteristic equation are complex. Or in other words, if W naught squared is greater than alpha squared. So if 1 over LC is greater than 1 over 2RC squared. The solution is then given like this. You have V of t, once again, solve for the voltage, equaling to some constant over here, e to the negative alpha t times the cosine of W dt, and that's where that WD comes in, plus beta 2, or I should B2, e to the negative alpha t sine of W dt. So at this point, you would know everything except, once again, your constants, and you would solve that using the initial conditions of the circuit. And the third and final response is critically damped. So if the roots are equal, or W naught squared equals alpha squared, or 1 over LC equals 1 over 2RC squared, then it's critically damped. And the solution is then V of t equals D1t e to the negative alpha t plus D2 e to the negative alpha t. And once again, you're solving for D1 and D2. So how do we solve for these? To solve for these, you want to use your initial conditions. So you're going to know some initial conditions of the circuit. This is just like first order, where you know, for example, sometimes you know the V of 0, the voltage across the capacitor. Oh, let me clarify real fast. Everything I've talked about right now, these equations, natural response of the circuit. So this is when their input is applied and let go. This is all natural response. So once the input's applied, you could maybe solve for the voltage at 0 across the capacitor. Maybe you could solve for the current through the inductor. Those initial conditions are what you would use to find your circuit. For example, the voltage at 0 is going to equal the voltage across the capacitor at 0, right? Because if everything is parallel, let's say it's fully charged. If it's fully charged, then the resistor acts like a resistor. The capacitor acts like an open. And the inductor acts as a short. Right. The voltage across this thing is across here, across the capacitor. One example how you could solve for that. And then, so you want to take your V of t, set your V of t equal to something that you solve for in your specific circuit. That gets you one initial condition. Then you set V prime of t equal to something. That gets you the second condition. And using those two, you can solve for your coefficients. The step response is very similar to the natural response. Except in the natural response, we're solving for the voltage. In the step response, we're solving for the current. So now we're solving for the current through the inductor over time, because the current through the inductor will eventually go to max. All the current will flow through the inductor because it turns into a short. So IL of t has to equal the final inductor current plus whatever the natural response form is. So note this is not the same numbers as natural response. Not the same. Let me clarify. Let me make it better. Not the same coefficients as natural response, but the exact same form with the same alpha and omega. So you would use these three things, underdamped, overdamped, critically damped, to get your form, and then you would solve for the initial conditions separately. It wouldn't be the exact same as when you solve for the natural response, but the process is the same, with the exception now you're solving for current. So like before, you're going to set your current at 0 equal to something that you already know and solve for one initial condition. And you're going to set your derivative current equal to something and solve for that initial condition. And that'll get you two equations for your two initial conditions, and you should be able to solve for both of them at once. Okay, let's move on to the series circuit. So the series circuit is when all three components are in series, right? Some resistor, some capacitance, some inductor. Once again, we're solving a second order differential equation. So the form of what we're solving for is the same thing. We're still solving for the roots of a characteristic equation with S1 and S2 equal negative alpha plus or minus the root of alpha squared minus W naught squared. What's important here is that alpha changed definitions. Alpha is now R over 2L. W naught is still equal to 1 over the root of LC, and WD is E still equal to the root of W naught squared minus alpha squared. It's alpha that changes. Much like the parallel case, there are still three responses. They are all the exact same, so I'm not going to rewrite them. But they have the same conditions. W naught squared is less than alpha squared. Remember that alpha is changing. Alpha is changing. But you can still have an overdamped, underdamped, or critically damped response. You test for them the same way. Test W naught less than alpha squared, W naught greater than alpha squared, W naught squared equals alpha squared. With this one change that alpha is different. Once again, once you have this you're going to solve for initial conditions. Before in the natural response, so this is natural, right? Before in the natural response of a parallel RLC circuit, we were solving for the voltage because the voltage was this thing that stayed the same across all three components. In the series, in the natural response of a series RLC circuit, the current is what stays the same. So we're solving for the current, where you're going to solve for your initial conditions with the current at 0 is equal to whatever initial condition you define, and then solve for the current prime at 0 equal to whatever your circuit has. The step response of the series RLC circuit, now we're solving for the voltage. And the voltage got the capacitor to be specific. Voltage of the capacitor we're solving for equaling the final voltage plus the same form as the natural series response. Same form, not same initial conditions again. And you would solve this conditions in the same way. Solve for VC at 0 equals something and V prime C at 0 equals something. So if you want to break down how would you solve a second order circuit, here are your steps. 1, you're going to solve for initial conditions across your nonlinear elements. So that would be your conductor or your capacitor. 2, you want to simplify your circuit. Try and get into a series or parallel form, because that's what you know how to solve, right? And then you want to solve for W naught and alpha. You want to ID your response type. So is it overdamped? Is it critically damped? Is it underdamped? You're gonna use the equation for the response. Solve for S1, S2, put that in, and then you have an equation with the only thing you don't know are the constants, and then you're going to solve for those using initial conditions, and then you will have a full answer. Okay, something else knows Dr. Chu. On the midterm, not the midterm, on his practice exam for the final, he likes to ask about, or it seems like he likes to ask about what the waveforms look like. So be comfortable with what each waveform looks like for critically damped, overdamped, and underdamped. So no critically damped waveform, no overdamped, and no underdamped. I do not know these off the top of my head, but they should be in your book. So make sure you know what each of these responses generally looks like. Alright. I would do an example, but I recently found out my examples I wrote down are actually done incorrectly. I was using the wrong equation to solve initial conditions. So I don't quite trust the way I did them. I haven't had a chance to go back and correct them. So let's get back. I'll get back to that then later. For now, let's move on to something that I'm more confident in the examples I have laid out. What was next in the agenda? Sinusoidal steady state. In any case, I didn't see Dr. Chu asking a full solution of a second order circuit. And note the hard part is finding these initial conditions. Okay, so this is with impedance. So everything previous to this chapter, you were dealing with DC signals. But with sinusoidal inputs, you're going to deal with, as the name implies, sinusoidal signals, alternating current signals. Each input waveform is a sinusoid. So our voltage is some voltage magnitude times the cosine of omega t, and it has some phase, right? And the current is some current with also a frequency and a phase. Note that the convention, at least my book used, is that every sinusoid is a cosine wave. So if you get a sine wave as an input, you can convert the cosine with a phase shift. So sine of omega t plus this phase equals cosine of omega t plus phase minus 90 degrees. And you can convert to cosine and everything's all great. And for a steady state sinusoidal circuit, the W out of the circuit will have the same frequency as the input. So W out equals W in. So if you know the frequency of the input, then your output signals will have the same frequency. And just as a reminder, the frequency is 1 over the period, which equals omega over 2 pi. So frequency in hertz and frequency in radians per second are different, and you need to convert between the two. So if they give you something in gigahertz, don't use that in this. Go here, find your W. Alright, so we would deal with sinusoidal steady state signals in phasors. We don't want to deal with all the cosines and sines. It's messy math. So to make our lives easier, we use this kind of shorthand, I guess. They're complex numbers that have information about the amplitude and phase of a signal. We don't care the frequency, because the frequency should be the same throughout the entire circuit. So we can go from a cosine signal to a complex number to a phasor and back and forth between all three. So let's say we get our input in cosine, as we normally will. So how do we go from cosine to phasor? So we have an input, let's say a cosine of Wt plus phase. We can convert back and forth to phasors like this: a phase, a angle phase. And this is really a complex, what this a phasor really is, it's the real part of a complex exponential. So of a e to the I Wt. That's what it is, where we omit the angular part. Not the angular part, we omit the frequency information. So that's what we're really doing here. But we can just not think about it and just go straight to phasor representation. It is the same thing. We can go from a phasor to a complex number because, once again, these phasors are complex exponentials. So you do it like you would any other complex exponential. We have a phase this. This is going to go to some complex number, x plus jy, where x equals a cosine phi and y equals a sine phi. And finally, we can go back. So from complex to phasor. Where x plus jy, we want to go from x plus jy back towards a angle phase. The angle is going to be the inverse tangent of y over x, and a is going to equal the root of x squared plus y squared. Just like how you do complex numbers, complex exponentials. So using these three, we can go back and forth between all representations of their signal, and we don't have to deal with any sinusoidal math, which is a blessing. So speaking of math, how do phasors exactly simplify the math? Well, when you're adding and dividing sinusoids, instead of dividing cosine of one signal over cosine of another signal, when we put it in phasor form, we'll say, let's say we're multiplying two signals. A phase 1 times B phase 2. This is like a complex exponential, so the coefficients multiply and the exponents add. And this can be easily converted to sinusoid, which is great. Or if we're dividing them, the coefficients divide, but the angles act like exponents. And so we get that. This is nice and easy. So this makes our life, well, easier. But why is everything complex? That's weird. Well, no. Before we didn't have to deal with complex resistances or impedances, but now we do because there's an AC signal. So each of the three components we know, resistor, capacitor, inductor, have what's called an impedance. Impedance is how a component impedes current flow, just like resistance, but now it's AC current flow. So a resistor has an impedance represented with Z, and its impedance is just a resistance. It's a linear element, doesn't matter. Some components have a phase difference across their inputs. V and I are in phase. And what I mean by phase difference is if we have a voltage waveform and a current waveform, this is out of phase. If they were in phase, they would overlap like this. And in a 90-degree phase is completely out of sync. That's what I mean by phase difference. A capacitor has an impedance of 1 over j omega c. So where omega is the same angular frequency we talked about earlier, and this is just a complex number. And the c is capacitance. There is a phase difference across the capacitor. V is going to lead I by 90 degrees. For an inductor, it's j omega L, and V is going to lag I by 90 degrees. And you can mess with phase differences in like Desmos. That's a good way to see it for yourself. Ohm's law carries forward for impedances. So the voltage is the current times the impedance across any component. And V and I are both sinusoidal signals in whatever form. Also important to note is that any technique you learn for DC signals applies here, still works. So all that superposition, nodal analysis, mesh analysis, you can do that all with complex numbers and phasors. Has not gone away. So to solve for a phasor question or a circuit with sinusoidal phasor inputs, let's talk about some steps or how I would recommend you solve these. So 1, convert all your signals to phasors. So all inputs, make them phasors. And identify what the frequency of your circuit is. And 2, it's all components. They'll be given to you with some sort of capacitance value. Make them impedances. And use the same W to make them the right impedance, because the capacitor and the inductor are frequency dependent. And that frequency is the frequency of the input, because as we set up here, the frequency of the output, for example, the voltage across capacitor, is the same frequency as the input. Go back down. Okay, so we've done step 2. 3, simplify when necessary. Don't make your life hard. You can combine impedances. And by combine, they combine in series and parallel, just like resistors. So if you have impedances in series, they combine to equivalent impedance, where Z prime equals the sum of all the Z's. And if you have a bunch of impedances in parallel, it can also combine to an equivalent impedance where 1 over Z prime equals the sum of 1 over all the Z's, just like resistors. And then 4, you use whatever technique you want to solve for what the question is asking for. Node, mesh current, complex algebra, phasors, use whatever. Solve for it and then convert it back to cosine form for your final answer, because that's typically what professors want. And so here I do have an example. So here's a circuit. And let's say there's some current here. A resistor. A capacitor. Let me read. This is terrible drawing. Let me redraw this. Marginally better. But it has an inductor, a capacitor, two resistors. This resistor is 120 ohms. This resistor is 40 ohms. This is 60 millihenries. And this is 12.5 microfarads. What we want to solve is for the voltage across this inductor, VO. And this is some current, where the current is a sinusoid. 500 cosine of 2000t milliamps. And we want to solve for the voltage at sinusoidal steady state, which is what we've been talking about so far. So, like I said in step 1, let's convert this input to a phasor. So, I can go to a phasor as, this should be 5,000, sorry. No, it should be 500. Oops. I was right the first time. So it's going to be 500 angle of 0 because there is no phase difference in this sinusoid. Milliamps. I'm going to convert to amps because I like my things in amps. 0.5 Alkan standard units, phase of 0, amps. Okay, that part's done. And what's our W? Our W is 2000. So W equals 2000, which I know because it's right here in front of the T. Now let's convert all our components impedances. And we want to make them equivalent impedances. My plan here is that I want to find the current going through here. And once I find the current going through here, I can use Ohm's law to find the voltage across the inductor. I want to make it, I don't want to deal with too much complex analysis, so I'm going to recognize that for this current source, if I combine these two impedances in series, and I combine these two impedances in series to make Z1 and Z2, this is a current divider. And then I can use the current divider formula to solve for this current, and then I can use Ohm's law to solve for this voltage. So that's the plan. Let's convert our components impedances. So the impedance of a 120 ohm resistor is just 120 ohms, just like the impedance of the 40 ohm resistor is 40 ohms. The impedance of the 12.5 microfarad capacitor, these are the capacitor, if we recall, is 1 over j omega c. This is 1, let's move the j to the top, multiply j by top and bottom. We're going to get negative j over omega is 2000, just 2000. And the capacitor is 12.5 microfarads, so that's 12.5 times 10 to the negative 6 farads. And when you use your calculator and multiply it out, negative J40. Let's repeat for the inductor. The inductor is J omega L. Omega is 2000. The inductance is 60 millihenries, so that's 60 times 10 to the negative 3 henries. And then we get J120 ohms. Let's add the components in series. So Z1 is the resistor and capacitor in series. So Z1 is the resistor, the 120 ohm resistor, plus the capacitor, which is a negative. So this should be negative J40 ohms. Z2 is the other resistor, so that's the 40 ohm resistor, plus the inductor's impedance, so 40 plus J120. So now we have both these. We have impedances, we have a currents. Let's use current division to find that current. So we want to solve for this current. So I is going to equal the big I coming in times Z1 over Z1 plus Z2. Right? If these resistances are the same thing. Let's plug all our numbers in. This is 0.5 phase 0. This is make that straighter. This is Z1, which is 120 minus J40. This is Z1 plus Z2, 120 minus J40 plus 40 plus J120. Let's simplify the bottom, and let's expand the top into a complex, let's expand the top into a complex number. So to expand the top into a complex number, it's going to be, let's go back up. How do we do that? We're going from phasor to complex. So it's going to be x plus jy, a cosine theta, a sine phi. Sorry, phi, not theta. I don't like how I'm saying theta. So it's going to be 0.5 cosine of 0 plus 0.5 sine of 0. And this is still 120 minus J40. And the bottom is W always given. Okay, yeah, so, I mean, it should be. So W if they have to give you an input signal, right? So if they have to give you an input signal in some sort of cosine form, they'll either say the input is a sinusoid. They'll either give you it. So they give you like the input is, in this case for current, I is some sinusoid with some magnitude, and cosine of Wt plus phi, where whatever's in front of T is W. Or they could say the frequency of the circuit is some number in hertz. And then you have to convert to W, where frequency equals 2 pi over W. I think. Let me make sure. Frequency equals W over 2 pi. This is why I check. I always write this down. But if they don't give you an input, I don't understand it. You probably wouldn't be able to solve the problem at all. Like, they have to tell you what the input is, right? I guess they can make you work backwards, but that would be a pain in the butt. At some way, shape, or form, you need to be given W, yes. So, may not directly given, but you'll find it out from the circuit, from the problem. Hopefully I answered your question. So we have 120 minus J40. Simplifying the bottom, this gets to 160 plus J80. Notice that cosine is 0, 1, sine is 0, 0. So this is just 0.5. Multiplying that out, we get 60 minus 20J over 80 over 160 plus 80J. So now we're left with this. This is the current, but we want to convert it to a phasor. So there are a couple ways to do this. You want to make this complex number division just one complex number. You can convert them each individually to phasors and then use phasor math, or you can use complex math to get them to one place. I'm going to choose to use complex math because less room for rounding errors, but you can do whatever you want. In this case, to get this to one phasor, we're going to multiply the top and bottom by the complex. So we're going to multiply by 160 minus 80J over 160 minus 80J. This eventually, after some multiplication, gets us 8,000 minus 8,000J over 32,000, which simplifies to 0.25 minus 0.25J. Now we can take this complex number to a phasor. Let's look at how we do that. I'll go back up. Complex to phasor, we use this set of equations. So the our phi is equal to tan negative 1 of negative 0.25 over 0.25, and A is going to equal to the root of 0.25 squared plus 0.25 squared. This ends up giving us 0.354 phase negative 45 degrees. But that's not the answer, because the question asks for the voltage across the inductor. This is the current. We want the voltage. So let's solve that. Voltage equals IZ. Ohm's law. Let's go back to complex form. This is 0.25 minus 0.25J. The impedance of the inductor we know is J120. So this is going to equal 30J plus 30J, which when we convert using these equations to phasors, we get that this is 42.4 phase 45 degrees. And now we can convert to cosine. So we can say this is now 42.4 cosine of W. W is 2000 in the circuit. This is 2000 T plus 45 degrees. And then that would be our answer. Okay, and so that was one example, but there's a number of problems that can be solved using sinusoid steady-state stuff. So let's move on to the next topic, which is, let me just check, Laplace analysis. So you should remember how to actually do the Laplace transform from differential equations. The things you need to really know and really remember are, one, remember how to use transform pairs. I don't think you have to memorize these. You should get a sheet on transform pairs. But what's the one thing you need to know? You need to know the partial fraction expansion. This is a skill you need to know how to do for Laplace transforms. If you don't remember, there's like a Paul's math notes thing online that's helpful on how to solve Laplace transform. There are two theorems that are useful when solving Laplace transform circuits. The initial value theorem, and you'll talk about these again in system and controls, but sometimes they crop up here. Value theorem, where the limit as t approaches 0 of ft equals the limit as s, our variable in the Laplace domain, approaches infinity of s f of s, is only if there is no impulse function at the origin, which I guess could happen in this class, so you have to watch out for that. And the final value theorem is basically the opposite. The limit as t approaches infinity of your time domain function is the same thing as the limit as your frequency domain function approaches 0. This is only valid if your circuit is stable, but I doubt you'll be given an unstable circuit in this class, so this should basically always work. In the book I am using, I don't know if this is true for Dr. Chu, all Laplace transforms are one-sided. That means for t less than 0, output equals 0. It basically means that your answer has an implied step function surrounding it. I don't know how you handle this. If it's imply, if you don't have to worry about it, if you need to put the step function after you solve for it, just be aware that this is a thing. And you should look at your own specific notes in class to see how to properly put down your answers. So, much like we transferred our circuit components to impedances in the previous topic, you're going to take your components and convert them to impedances again, except this time your variable is S instead of JW. So JW goes to S. And you can redraw entire circuits. So resistors stay the same. but initial conditions are now modeled in the circuit. And this is what I mean. So let's say we have an inductor. An inductor can have some initial current and has some inductance, right? We can transform this into an inductor. So I said before J goes to S, so this inductance will be now SL. This is normal. What's new is that the initial condition across the inductor can be represented in two ways. One, with a voltage source with a value LIO, or we can take our inductor and put it like this. So this current source and this voltage source come from the initial conditions across the inductor, and these are now physically represented in your Laplace domain circuit. And then you could solve for it as normal and treat it like a normal voltage source, which is the cool part of Laplace transform. Why it's so useful. The same thing for capacitor. Capacitor has some initial voltage and a capacitance. We can transform it to the capacitor where its impedance is 1 over SC as expected, but you can also have a source here. Or we can also have a current source. So you redraw your circuit as follows, and then you solve for it. So let's talk about actually some more things to talk about. One, the transfer function of a circuit. The transfer function is the output in the Laplace domain over the input in the Laplace domain. I'm not sure if you're asking anything about this. It's just good to know. Okay, now move on steps. The steps to solve the Laplace transform circuit are: one, you're going to convert components to the Laplace domain. Apply Laplace transform sources, and completely redraw the circuit according to all this stuff over here. Once you have redrawn the circuit, you're going to solve it using any circuit technique you know of, like mesh current, node analysis, etc., etc. And then you want to use the partial fraction expansion plus the inverse Laplace transform to go back to the time domain. And that's your answer. So you go from your original circuit, you convert everything into Laplace, you solve for your output in Laplace, and you convert back the time domain to get it back to where you originally had it, where you want it. So yeah, let's do a quick example. Let's find a circuit that looks like this. One millifarad, which is enormous, by the way. 35 ohms, 250 millihenries. And we want to solve for this voltage. So let's convert to Laplace. If you know, your table should tell you that a step function goes to 1 over s. So that's where I'm going to get that from. Let me say that right now. So this is going to convert to 60 over s. Note that none of these have initial conditions. Let's assume they're all 0. So I'm not going to draw any initial condition circuits. I'm going to it's some impedance over here. The impedance is 1000 over s, coming from the capacitance, it's or this capacitance equals 1 over SC, and C was 0.001, 1 over 1000, so 1000 over S. This resistor stays 35 ohms because it's a resistor, and this inductor becomes 0.25 S. Again, L equals SL, and 250 milli is 0.25 normal. So to find V out, once again, I'm going to use the current divider formula and Ohm's law. So let's label this as I1, and this is our V out. V out equals I1 times the impedance of the inductor. I1 can be solved for using a current divider. So that's the input current. And I'm going to convert this to amps real fast to match units. So that's 0.06 over S times the opposite impedance over their impedances added. And these two are in series, so they just add like that. And this gets multiplied by the impedance of the inductor. And when you do all that algebra, which I will skip, you're going to get 60 over S squared plus 140S plus 4000. And this is where you will want the partial fraction expand, because your transform table won't have an expression for this. You want to get it into a form of A over S plus or minus something plus B over plus or minus something. The first step to partial fraction expansion, step 1, is to factor the denominator. And I'm going to do that in my head because I have it written down beforehand, but you would do it any way you know how to. This would be S plus 40 times S plus 100. So once you factor the denominator, you want to make this equal A over S plus 40 plus B over S plus 100. How I do this is I multiply this entire expression by this denominator. This leaves me with 60 equals A times S plus 100 plus B times S plus 40. And I say, what if, coincidentally, S equals negative 40? Well, if S equals negative 40, this has to be true. So we can solve for that, where 60 equals A times negative 40 plus 100 plus B times negative 40 plus 40. Oh, this is now 0. 60 equals A times 60. A equals 1. So I chose negative 40 to cancel out that right-hand side expression so I can solve for A. Now I'm going to do the same thing to solve for B. Let's say S equals negative 100. 60 equals 0 plus B to the negative 100 plus 40. And B would equal negative 1, right? Because this equals negative 60. So now we have solved for A and B. We get that V out and a function of S is 1 over S plus 40, that was our A, plus a negative 1 over S plus 100, that was our B. And now these expressions should be in your Laplace transform table. So these are both exponentials, where the general form for an exponential in the Laplace transform is some 1 over S plus alpha equals e to the negative alpha t when you're going the Laplace transform. So v out of s, we can transform to v out of t equals e to the negative 40t minus e to the negative 100t. And because this is all one side, I'm going to surround this by a u of t, but I don't know if pressure requires that. And so this similar procedure is solved for generally the entire thing. Okay, so that's, I guess, everything. It's a quick overview of the second half of the semester. I don't think that Chu asked any in-depth questions as far as solving things. His stuff he seems mostly theoretical, but op amps. Oh, I forgot about op amps. Oh, let me do those. Okay, we'll finish off with op amps. He knows us about those. Op amps. Okay, so an ideal op amp looks like this. A nice triangle. We have some negative input, some positive input. We have voltage rails and an outputs here. Op amps, they amplify the difference between their positive and negative terminals up to the voltage rails as input power. So to analyze these in linear operation, we're going to assume the two golden rules. So golden hello? Oh my goodness, decided to slow down dramatically. There we go, golden rules. Okay. We're going to assume two things. One, that the current into the input terminals is 0. What we're assuming is that the op amp is an infinite input impedance. And we're also assuming that the voltage difference between the terminals is 0. So V plus equals V minus. To solve, one, you're going to apply the golden rules. And then two, wow. Two, you're going to use node voltage to solve the circuit. Or really any technique, I would suggest node voltage. Yes, my computer is dying, sorry, that's why I'm saying these things. I should finish up before it overheats. Let me do an example. And I know that there are like typical op amp configurations in the book that you can memorize. I would advise knowing how to solve for the gain by hand instead of just memorizing the configurations, because he could just ask you something that's not standard, and then you'd be screwed. So this is how you solve for any circuit. So let's see a circuit looks like this for op amp. A resistor, ground. Here is our op amp. Feedback resistor. Ground, and one more. Okay. This is 5 kilo ohms. This is 10 kilo ohms. This is 8 kilo ohms. This is 6 kilo ohms. This is 3 kilo ohms. This is grounded, of course. This is negative 5 volts, and this is 6 volts. Okay. Here's the op amp. We want to find I naught. Basically, you want to find V out first, and then we can find I naught. So the first thing we want to do is find use the golden rules. So for the golden rules, the current entering. Let's write no voltage equations for our terminals, our positive and negative terminals. So for the positive terminal, let's write no voltage. It's 6 minus V plus over 10,000 minus some current going into the positive terminal minus V plus minus ground over 5,000 equals 0. But because of our golden rules, this current going to the terminal is 0. So let me draw the currents here. Current, right? But because of the golden rule, that goes away. The second equation is at the negative terminal. We can say that negative 5 minus V minus over 25k. 25k. I must have mislabeled this. And this is minus I minus V plus minus V out over 6,000. Once again, the golden rule tells us this is 0. We can solve for the positive terminal because the only equation is V plus. Using algebra, your favorite algebraic method, we're going to get that V plus equals 2 volts. Okay, now we apply the second golden rule. V plus equals V minus. We plug that into here. Now this equation is reduced to negative 5 minus 2 over 25,000 minus negative, not negative, minus 2 minus V out over 6,000 equals 0. And now this equation only has V out. So we can solve for V out equals 16 volts. I out equals V out over the resistance, which equals 16 over 8K, which equals 2 milliamps. So to reiterate, we wrote node voltage equations for the positive and negative terminal. We used the golden rules. First, that the current going into the terminal is 0, and then that the voltages at the terminals are the same. Using that, simplified our equations to we're able to solve for V out directly. And once we solve for V out, we can solve for that I out. Generally, that's going to solve for V out though. In this circuit, the gain is our V out was what? Our V out was, so gain equals V out over V in. And this input is a bit complicated, but yeah, I don't know what the input we consider here. If it'll be 6 minus negative 5, but the output is larger compared to both of our inputs, negative 5 and 6. Oh, I guess the input would be amplify the difference between the two terminals, right? So 6 minus a negative 5, that's 11. So it went from 11 to 16. So to amplify the difference of 11 to 16. So the gain would be that number, 16 over 11. And you could solve this for a variety of different op-amp configurations. And I guess that's it for op-amps. I guess that's it for the whole review. Unless you have specific questions, or you want me to go back over something. We did this, and this wasn't really covered according to you guys, so I'm not going to go over it. It's similar to Laplace stuff anyway. And any of the material before this should be in the first test review. So you can go back and watch that, which should also be on the YouTube channel. And I've also done like prior test reviews in the past. You could look at those if you want more examples. Although keep in mind that, like I said, second order circuit examples were incorrect. I did those wrong. Don't look at those. So I'll wait for the delay to catch up, and then I'll wait a couple seconds. And if no questions, I'll end the review. Well, if there are no questions, good luck in your exam. Yeah, make sure to look at this practice final. If it's anything like the actual final, it's a good thing to prepare for it, because get used to solving those types of questions. They look to be mostly theoretical, and I mean, I did a lot of like calculation, number, but he doesn't seem like he's doing much of that, which is great. So prepare for those kind of questions would be my advice. Good luck, and